We will start in a couple of minutes. Okay, I will share the slides. Is the slides visible? Okay. Good evening, all. Welcome to NPTEL PMRF tutorials of the course Pericyclic Reactions and Organic Photochemistry by Professor Eschenmoser-Claisen from IIT Madras. Myself, Anisha Suresh, PMRF TF for this course from IIT Bombay. So, in last week, that is in week 5, Sir have mainly discussed regarding some of the sigmatropic rearrangements, which includes Wittig rearrangements and all, and some higher order rearrangements, followed by chelotropic reactions, where extrusion of some small molecules will be taking place. So, in this tutorial session, we will be discussing some questions based on sigmatropic rearrangements, followed by some based on chelotropic reactions. So the first question is predict the co-rearrangement product of this reaction. So they have mentioned it is a co-rearrangement. So we know co-rearrangement is a 3,3 sigmatropic rearrangement. Okay. So how the mechanism will be taking place? So this is a 3,3 sigmatropic rearrangement. So we can number it like 3, 2, 1, 3, 2, 1. Okay, so the arrow pushing will be like in this fashion. this 1 bond will be breaking, and it will result in the formation of the final product. So let us see what is the final product. So this is 3, 2, 1, 1, 2, 3. A new bond is formed between carbon 1 and carbon 7, which is this, and this 6 7 double bond is shifted to 5 6, as you can see here, and this 3 5 bond is broken, and this a new double bond is formed between carbon 2 and 3, and the double bond on carbon 1 and 2 will be converting into single bond. Okay, so this is the mechanism for the co rearrangement that is taking place on the substrate upon heating. Is this clear?
Yes, clear.
Okay, now coming to question number 2. So predict the product of this reaction. So from seeing this substrate, it is obvious that it will undergo a 3 3 sigmatropic rearrangement, like 3 2 1 1 2 3. So how the reaction will be taking place? Please try to work it out. So for our convenience, we can draw it like a chair conformation. So here the OH is above the plane, hydrogen will be below the plane, and the two vinyl groups will be, this will be above the plane and this will be below the plane. Okay, now if we will try to draw the mechanism, 3 2 1 1 2 3. So the arrow pushing will be like in this fashion, this bond will be breaking, so it will result in the formation of OH will be there, hydrogen will be there, this bond is broken now, and between these carbons a new bond is formed, and the double bond is formed in these two carbons. Okay, so this can undergo tautomerization, and it will result in the formation of here a ketone and here a double bond. So this we can redraw like this. So this will be the final product that is forming after the 3 3 sigmatropic rearrangement. So here what is taking place is a 3 3 sigmatropic rearrangement. So first a 3 3 sigmatropic rearrangement will take place, resulting in the formation of this intermediate, which will undergo a tautomerization, giving the final product. Is the mechanism clear?
Yes, clear.
Okay. Now going to the next question. So here, predict the product of the following Claisen rearrangement. So we know that this is also a 3-3 sigmatropic rearrangement. So we can number it like 3, 2, 1, 1, 2, 3. So what will be the mechanism? Please try to work it out. Able to draw the product?
I have written the product, but I don't know it is correct or wrong.
Okay, okay. I will just draw the mechanism. So a new bond will be formed. The arrow pushing will be like in this fashion. This will shift here and this bond will break, resulting in the formation of an aldehyde. So this system, decalin system will be remaining as it is, and this whole group will be shifting to this carbon. So this will be 3, 2, 1. Okay, and a new bond will be forming here. Double bond will be forming here. Is this the product that you got?
Yes, correct.
So this is also an example of 3-3 sigmatropic rearrangement. So this is how the reaction is taking place. So here they have highlighted the atoms that are involving in the 3-3 sigmatropic rearrangement. So we can label it like 3, 2, 1, 1, 2, 3. So if we do a bond rotation such that the two double bonds will be coming in proximity, then after that the shift arrow pushing will be in this fashion. This bond will be breaking, resulting in the formation of the aldehyde. Clear?
Yes, clear.
Okay. Now, coming to the fourth question, predict the product of the following Claisen rearrangement. Uh, and we should be, after drawing the Claisen rearrangement product, we should be careful that we will be getting the most stable product. So, please try to work it out.
Are we getting 2-propylene phenol?
Hmm?
2-propylene phenol
Okay.
or orthopropylene phenol?
Yeah, yeah. I will just draw the mechanism. We will see. So we can number it like 3, 2, 1, 1, 2,
Two, three.
3.
Yes.
Then we can draw the arrow pushing like, so it will result in the formation of a ketone and
And
one
here, three membered. Yes.
allyl group.
Hmm. But this is the not a stable one. Here we have to this product. It is going to get it aromaticity again.
Yeah. So here the aromaticity is lost. So aromaticity, if it is gaining, means it will be giving a more stable product. So this proton will be lost and it will
OH.
result in the
Right.
formation of OH. A tautomerism will be taking place here. Ketoenol tautomerism sort of will be taking place, resulting in the formation of this as a final product.
Okay.
Okay.
Yes.
Now coming to the fifth question. So this is a name reaction. It is also coming under Claisen reaction only, but it is having a particular name reaction. So please try to work it out. We are having an orthoester, and in the presence of this allyl alcohol, it is converting into this alpha, beta, gamma delta unsaturated ketone. Able to do it?
Yes. This allyl vinyl ether. We will get
Hmm. So what is the exact name reaction?
exact name reaction.
So the
This will come under similar to
orthoester, na?
cope rearrangement.
It is a Claisen rearrangement only. So it is
Yes.
particularly known as Johnson-Claisen
Okay. Okay. John's.
rearrangement. Okay. Now we will
Okay.
see the mechanism. So first, in the presence of acetic acid, this OMe will get protonated, and once a lone pair of OMe will a group of methanol, a molecule of methanol will be eliminated, giving this as the intermediate. Now the allyl alcohol will attack at this electrophilic carbon center, and this double bond will be opening up for neutralizing the positive charge. So we will be getting this
Yes.
intermediate, and then this methanol protonation will be taking place, and once a lone pair of oxygen will fall, methanol will get eliminated, resulting in the formation of this intermediate. Then acetate will be abstracting one of the proton, uh, leading to shift of this double bond and neutralizing this positive charge, leading to formation of this allyl vinyl ether. Then this will be undergoing a 3-3 sigmatropic rearrangement, like 3, 2, 1, 1, 2, 3. It will result in the formation of this gamma delta unsaturated ketone as a final product. Is it clear?
Yes.
Okay, so this is known as Johnson-Claisen rearrangement. So here, allylic alcohol and a trialkyl orthoacetate will be present, and in the presence of catalytic acid and under heating condition, it will result in the formation of gamma delta unsaturated ester. Okay, so this is what we have to keep in mind. This is what makes it different from other Claisen rearrangements. Okay, trialkyl orthoacetate. So the Johnson-Claisen rearrangement is an organic reaction where an allylic alcohol is heated with trialkyl orthoacetate under mildly acidic conditions to produce gamma delta unsaturated ester. So the reaction begins with protonation of one of the alkoxide groups of the orthoacetate. As we have seen, one of the methanol is OMe is getting protonated and methanol will be leaving. So the protonated alkoxide is then released as a molecule of alcohol and forms an oxonium cation, which is then attached by the alcohol. So we have seen that this oxonium cation will be forming and the alcohol will be attacking on that oxonium cation. Then proton transfer steps then follow, protonating another alkoxide group that is then lost as alcohol and forms another oxonium cation. So here proton transfer is taking place, and one molecule of methanol is again eliminating, resulting in the formation of another oxonium cation, and then a deprotonation step then produces a 1,5-diene intermediate which undergo a Claisen sigmatropic rearrangement to produce a final gamma delta unsaturated ester product. So this is the mechanistic pathway that is taking place in Johnson-Claisen rearrangement. Clear na?
Yes, clear.
Okay. Now coming to next question. So here, instead of the orthoester, we are having an amine. So this is also a different type of Claisen rearrangement, and I think sir have discussed in the lecture. Could you recall?
No, actually, I didn't came to that video.
Okay, okay,
I'm in the previous video still.
okay, okay. So this is known as Eschenmoser-Claisen
Eschenmoser.
rearrangement. Okay. So let us see how the mechanism is taking place. So OMe NMe2 in the presence of acetic acid, one of the OMe will get protonated and it will get removed, resulting in the formation of this iminium ion. Okay,
Yes, okay.
now the allylic alcohol will be adding onto this iminium, resulting in the formation of NMe2 OMe OH plus and the allyl group. Now proton transfer will take place. A proton transfer will take place, resulting in the formation of OMe H plus. Again, another molecule of methanol will be eliminated, resulting in the formation of one another iminium ion, like this. Now, what will happen? The proton abstraction will be taking place in the presence of this acetate. Here, the proton will be abstracted and it will result in the formation of NMe2O, like this. Okay. So this is the precursor that will undergo a 3,3 sigmatropic rearrangement. Like if we number 3, 2, 1, 1, 2, 3. Okay.
Just 1 second.
Hmm. Able to follow?
Yes.
So this is our starting material. In the presence of acetic acid, one of the O-methyl group will be getting protonated. Then once a lone pair on the nitrogen will fall, this methanol will be getting removed, minus MuOH. And it will result in the formation of this iminium ion. Then alcohol will be adding to the electrophilic center of the iminium ion, resulting in the formation of this tetrahedral intermediate. Then here a proton transfer will take place and it will result in the formation of this intermediate. So again when lone pair on nitrogen will fall, another molecule of methanol is getting removed, leading to formation of the second iminium ion species. Here a deprotonation step will be taking place, resulting in the formation of this key intermediate which is undergoing a 3,3 sigmatropic rearrangement. Okay.
Yes, understood.
Now, after undergoing a 3,3 sigmatropic rearrangement, what is taking place? So, this is our 3 in Me2 double bond O, and here a CH2. Here already one CH2 is there, again one CH2, one second, CH2, CH2, like this. Okay, gamma delta unsaturated amide will be forming in this case. Mechanism is clear?
Yes.
Okay. So this Eschenmoser-Claisen rearrangement. So here we will be having an allylic alcohol and N-dimethyl acetamide dimethyl acetal. So it will result in the formation of a gamma delta unsaturated amide. So Eschenmoser-Claisen rearrangement, it is an organic reaction where allylic alcohol is heated with this N-dimethyl acetamide dimethyl acetal to produce a gamma delta unsaturated amide. This is the final product. So the reaction begins with release of a methoxide group as we have seen from the starting amide starting material to produce an iminium cation which is then attacked by the alcohol. So here a first iminium cation will be formed and the alcohol will be attacking on that iminium cation. Then what will happen? Proton transfer steps then follow, which place the proton on the remaining methoxide group, which is then released as a molecule of methanol, and another iminium cation is formed. So after that, a proton transfer is taking place on this tetrahedral intermediate, and again one iminium cation will be forming, leading to removal of another molecule of methanol. Then deprotonation with methoxide produces a 1,5-diene intermediate which undergoes a Claisen sigmatropic rearrangement. So here either OMe minus will be present in the medium or OAC minus will be present in the medium which can abstract the proton, and it will result in the formation of this intermediate, this key intermediate that will undergo a 3,3 sigmatropic rearrangement which is also known as Eschenmoser-Claisen rearrangement, which will result in the final amide product. Okay.
Okay.
Hmm. Now, coming to the next question. What is the product of this Wittig rearrangement? So, in this modules, I have discussed regarding the Wittig rearrangement. So, it is a sort of 2 3 sigmatropic rearrangement. Please try to work it out. So, in the presence of butyl lithium, what is the first step that is taking place?
That abstraction of proton is the proton.
Abstraction of this benzylic proton will be taking
Inside
place.
the proton. Yes.
So, in the presence of butyl lithium will abstract one of this proton, resulting in the formation of this
Minus. Yes.
right. Now,
After this hydrolysis.
now we can number it like 2, 1, 1, 2, 3. A 2 3 sigmatropic rearrangement will be taking place here. Okay.
Okay. 1 second.
Now, what is the product that is forming? pH is there, O minus is there, and ACH2. If we number each carbons, then it will be more easier to get. So if we number it like 1, 2, 3, 4, 5, 6. Okay, we numbered all groups. So 6, and this is 5, this is 4. So 3 4 bond is getting broken, and in 5 and 1 a new bond is forming, and nearby one. Okay, this will be the numbering, and in presence of H3O plus, protonation will take place and it will lead to formation of OH. Clear?
1 second. O minus pH. Okay, clear.
So this is the mechanism. First, deprotonation will be taking place. Then this O minus will be attacking on this alkene. Double bond will be shifting. This 3 4 carbon oxygen bond will break, resulting in the formation of this intermediate. And in the presence of H3O plus, O minus will get protonated, leading to the formation of this benzylic alcohol.
Yes. Okay, understood.
Okay. Now coming to question number 8. Identify the retron in the following molecule, then draw the starting material, go back only one step that would yield the target. So, this is our product. They are asking us to find what is the starting material that will result in the formation of this product. So, we can understand that this is a 1,5-diene and it will be the result of a 3,3 sigmatropic rearrangement. 1, 2, 3, 4, 5. 1, 5 diene. And it is obvious that it is a product of a 3, 3 sigmatropic rearrangement. So, what will be the starting material that is giving this final product? Please try to work it out. So, just we need to do is 3, 3 sigmatropic rearrangement again for finding out the starting material. So, we can number it like 3, 2, 1, 1, 2, 3.
Okay.
So, a bond will be forming between these two carbons, and this bond will be breaking. Okay. So, this will be the final product. So, this is a retrosynthetic arrow because this is the product and this is the starting material now,
Yes.
showing that we are drawing this retrosynthetic arrow. So this here a 3, 3 sigmatropic rearrangement is taking place on the starting material, resulting in the formation of this product. So if we number the carbons like atoms like 1, 2, 3, 4, 5, and 6, a bond will be forming between 1 and 6. This double bond will be shifting to 5, 4, and thus 4, 3 bond will be breaking, resulting in the formation of a double bond on 2 and 3 atoms. And if we redraw it, just flip it and draw, it will be like this. Okay,
Yes. Okay.
follow the numbering. Clear na?
It is clear. One second, ma'am. I want to write it.
Okay.
Done.
Okay. So just this is a six-membered ring that they are following. One, two, three, 4, 5, and 6. Okay, that is this one.
Yes.
And the three like bridgehead which is coming is this part. This part. This part
Yes.
is the bridgehead that is coming, and this these two carbons, these two groups are coming on the sixth carbon. Okay.
Okay.
That is how they have redrawn this. So this, when it will undergo a 3,3 sigmatropic rearrangement, it will result in the formation of this product. So sometimes they can ask after giving the product what is the starting material. Maybe I think one question we have discussed in last week. Similarly, they have given the product eliminate something and they are asking to find the starting material. So doing a 3,3 sigmatropic rearrangement, we will be able to get the starting material.
Okay.
Now coming to the question number 9. Propose a mechanism for the following reaction. So this is a reaction that is involving 4 steps and out of which 2 are sigmatropic rearrangement. So this is the starting material and this is the final product that is forming. Just this O is getting replaced by NBN. Please try to work it out.
He has intersect.
Able to?
First, what we are going to get this four-member drink with one this vinyl system and one is with aldehyde.
Hmm. So what is taking place there first?
There, this 3,3 sigma tropic.
Yes, 3,3 sigmatropic rearrangement will be taking place. So it will give
Yes.
a product. So here this is a asavitic reagent. Na?
Yes.
So that
Here,
aldehyde which will be
after
forming.
3,3 sigma tropic rearrangement, we are going to get the aldehyde component. That aldehyde component, it will react with this one.
Yes, yes, yes. Then again it will undergo a like a 3,3 sigmatropic rearrangement for giving the
Okay.
final product. So let us see the mechanism. So it is like this.
Yes, first I got this. That we
3,
have to do as a Wittig.
1, 1, 2, 3. A Claisen rearrangement will be taking place in this fashion, resulting in the formation of this aldehyde. Then Asa-Wittig reaction will be taking place. So this is a Wittig rearrangement. It will react with this aldehyde, resulting in the formation of this product. Okay. So they have considered this also as a step. That is why they have mentioned it like 4 steps. Okay. This
Uh,
required also, but it is a single step ideally.
hmm.
Then again a 3,3 sigmatropic rearrangement will take place between these atoms like 3, 2, 1, 3, 2, 1. So it will attack here, this bond will shift here, this bond will be breaking and it will give the final product. Clear na?
Yes, understood.
Okay. So just a Claisen rearrangement is taking place, resulting in the formation of this four-membered ring with substituted vinyl group and aldehyde. On that aldehyde, the azavitic reagent will be reacting, giving first a four-member transition state which will cleave, leading to removal of pph3o, and this as the product. And this is a substrate that will undergo again asa-Claisen rearrangement, and that will result in the formation of our final product. Now, coming to the next question, what product is generating in each of the following reaction? So this is a 1,3 dipolar cycloaddition question.
Yes, one three dipolar.
This is one N-oxide reaction and this is nitron reaction. So this is an intramolecular version of 1,3 dipolar cycloaddition reaction. So you try to work it out, then we will see what is a product that is forming.
The first one, five-membered nitrogen and oxygen containing compound.
Hmm.
Second one, second one is the intramolecular 1,3 dipolar reaction.
Yes, yes. So we will see the mechanism. So in the first case, this is the one dipole and this is the dipolophile. So the O minus will be attacking on this position and this bond will be attacking at this carbon, leading to neutralization of the positive charge on this nitrogen, and it is forming an isoxazole. So this system is known as isoxazole, which is containing this five-membered nitrogen and oxygen with double bonds. Okay, that's only you got now.
This I got, but like one doubt I have.
Hmm.
I substituted this R1 here and R2 in the next position.
This position that
Yes,
also
why
is
we cannot
possible.
write this R2 just opposite manner? I
Okay,
just wrote it ulta.
like this is also possible, and as you told, this other one, right? N O R1.
Yes, I wrote like this. Then
Okay, it depends.
examination, how he'll confirm which one is the major product.
It depends upon what is exactly that group coming. Now maybe we can think of the sterics part. Like if R1 and R2 are coming together, it can lead to more sterics. That is why this is forming as a major product. Actually, if we exactly know
But
what is
like,
this
see, what I thought, I'm just telling you,
hmm,
this O minus, it will attack where the electron density will be less in the alkene.
okay.
And that one carbon which is connected with R2,
Hmm.
that carbon, it has more electron density compared to the other one, that other carbon. That is why I thought it is O minus, it should
But
attack to
we
the
should be
this
knowing
carbon.
exactly what is this R2 na, for telling about electron density.
Why that R1, generally we are taking it as a like alkyl group. So
Hmm.
alkyl group mostly it will push the electron.
Hmm. So it will give more electron density at this ender only, right?
Yes, here, the carbon which is attached to R2.
No, no, no.
Hmm.
Because of inductive effect, it will be having more electron density at this ender, right? If it is an alkyl group. If it is some electron withdrawing group, then this ender will be having less electron density.
Yes,
If it
electron
is
density.
electron donating group, this ender will be having more electron density. So it depends upon what is R2. Now maybe we can consider steric factor. If R1 and
Oh,
R2 are coming and it is causing some steric hindrance, that may be why this is preferred.
okay.
Okay.
Oh, okay.
Now coming to the next question, which was intramolecular 1,3 dipolar cycloaddition reaction. So for feasibility, for the like dipole and the dipolorophile coming together, we can redraw it in this fashion. Okay. So this is the dipole part. This is the dipolorophile part. So it will
Yes.
attack in this fashion, resulting in the formation of this bridged sort of system. Okay.
Okay.
Now coming to the question number 11. So this is based on chelotropic reaction. So in chelotropic reaction, it is also a concerted mechanism, but a small molecule will be getting eliminated from the system. Here SO2 is a small molecule that is getting eliminated. That whatever molecule is getting eliminated, it should be stable as its own. So that is the driving force for this elimination reaction to take place. Okay.
Yes, okay.
So how it is taking place? Here this bond will shift here, this bond will shift here. And like this. So SO2 is getting removed. These two bonds are getting clean. SO2 is getting removed. And what is the product that is forming? Double bond Et, double bond Me. Okay. So
Yes, I got the same.
if we are knowing the mm, exact stereochemistry of this Et and Me, then according to Woodward Hoffman rules, we can like this exactly we don't know what is it E or Z, we don't know. Okay.
Okay.
Once the stereochemistry is given according to Woodward Hoffman rules, we can predict the stereochemistry of these ethyl and methyl. Whether it is E or Z, we can define after that. So this is how a chelotropic reaction is taking place. Okay. So just for explanation, I have kept the slide. This is the mechanism that will be taking place, giving Et Me plus one molecule of SO2 will be getting removed. Clear na?
Yes, clear.
Now coming to the next question. What is the name of the following pericyclic reaction? So this is the starting material. It is giving this product and one molecule of nitrogen. So whether it is known as cycloaddition reaction, sigmatropic reaction, electrocyclic reaction or chelotropic reaction.
Chelotropic.
Yeah, because a small molecule of nitrogen, which is a stable molecule, is getting removed. This is known as a chelotropic reaction. So the mechanism is like, okay,
Yes.
result in the formation of this diene, and one molecule of nitrogen will be removed. Now coming to the next question. Complete the following reaction sequence. So this alcohol we are having, it is treated with pH SBr. Bromide of thiophenol in presence of pyridine. So it will result in the formation of A substrate, and that is undergoing some rearrangement resulting in the formation of B. What will be the rearrangement that is taking place here? Please try to derive the structure of A first.
And as I A, what we are going to get this release of HBr, and that the rest part it will get attached with the oxygen.
Hmm.
OSPH. First we are going to get that.
Yes, yes. Then it is undergoing a 2-3 sigmatropic rearrangement.
2,3 sigma
Yeah,
tropic rays.
to give B.
Okay.
So this lone pair on oxygen will attack on the sulfur, bromide will be leaving.
Yes.
It will result in the formation of OH plus SPH. So this pyridine will be abstracting this proton, leading to formation of OSPH.
pH. And next.
Next, this is a 2-3 sigmatropic rearrangement. We can label it like 2, 1, 1, 2, 3. Okay, so this will attack here, and a sulfoxide will be forming. Okay, like this. Nucleophilic substitution reaction will be taking place first, resulting in the formation of this A. Then upon heating, it will undergo a 2-3 sigmatropic rearrangement in this fashion. Lone pair on sulfur will be attacking on this alkene. It will shift here, and a sulfoxide will be forming. Clear?
Yes, clear.
Okay. Now coming to question number 14. So this is having three sub questions. So these all are examples of chelotropic reactions only. Just for working out how the chelotropic reaction is taking place, it will be easier. So first, this is a two-step reaction. First, chelotropic reaction will take place, leading to formation of a diene, and it will undergo Diels-Alder reaction with the dienophiles that are given here, le- leading to formation of the final product. So you can try to draw it first. able to do.
Yes, first and second I got first chelotropic, then dialsilder.
Hmm. Similarly, only with third case also.
In the third case, carbon monoxide it will get released.
Carbon monoxide is getting removed. So let us see the mechanisms for each. For the first question, this is the starting material. So it will undergo a chelotropic reaction, as you can see by the arrow pushing. This double bond is shifting here. This bond is coming to sulfur and this bond is breaking. So the sulfur dioxide is getting removed. SO2 is getting removed as gas, and it will result in the formation of this diene. And we have been given this dienophile. So it will undergo a 4 plus 2 cycloaddition or Diels-Alder reaction. So we can draw like this: CO2 CH3. It will result in the formation of, okay, this will be the final product. This you got now. First, a chelotropic reaction is taking place on this sulfone. It will eliminate a molecule of SO2, resulting in the formation of the diene. So we are having the diene in situ generated, and the dienophile is already given. So it will undergo a 4 plus 2 cycloaddition reaction or Diels-Alder reaction. Like this is the arrow pushing, and it will result in the formation of this product. Okay.
Yes, okay.
Now coming to the second part. So here also a chelotropic elimination reaction is taking place. So the arrow pushing will be in this fashion. Molecule of SO2 will be getting eliminated, and it will result in the formation of this diene. So diene is there, and this is the dienophile. So arrow pushing can take place in this fashion, resulting in the formation of this final Diels-Alder product. Okay. Able to follow? Is there any doubts in this question?
No doubt.
Okay. Now coming to the last part of this question. In the previous cases, SO2 was getting removed, but here a molecule of carbon monoxide is getting eliminated. Okay, so the chelotropic reaction arrow pushing is like in this fashion. It will result in the formation of this diene, and this is our dienophile, this alkyne. So the arrow pushing will be taking place in this fashion, resulting in the formation of this final product. Okay.
Yes, okay.
Mm. Now coming to the last question of today's session. Identify A and B in the following scheme. Suggest mechanism for formation of B from A. So in the presence of MCPBA, what will be happening to this?
Epoxidation.
Like it will undergo oxidation. Epoxidation won't be possible. The sulfur is there, no? It will undergo oxidation. That
Okay,
is the
okay.
formation of
Understood.
ketone. So this is like aromatic species. So it will not be that much prone for Diels-Alder reaction. So after epoxidation, this A will be forming sulfones that can undergo a Diels-Alder reaction with this dienophile.
Yes.
So please try to work it out. So let us see. In the presence of MCPB, the sulfur is getting oxidized to the sulfone. Okay. Then this is a diene. This is a dienophile. It will undergo a Diels-Alder reaction, resulting in the formation of this intermediate. Now it can undergo a chelotropic elimination, resulting in the formation of this substituted benzene. Okay, first this will be formed. Aromaticity should be regained. So for that, this SOP PHSOH will be getting removed. There is other possibility also, I guess. Here also, no, 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 no. Here, chelotropic elimination is not possible. In this sort of system, only chelotropic elimination will be possible. Fine.
Yes, I understood.
So this was initially diene, but this is not reactive as a Diels-Alder reaction will result in loss of aromatic. Okay, so that is not reactive towards Diels-Alder reaction.
Understood.
So was all questions clear?
Yes. Today's all question I got that answers also.
Okay, okay. So thank you. Today this was the last question we were having. So if you are having any doubts regarding lecture, you can feel free to ask.
Okay, actually I have to attend more lectures.
Okay.
Still in fourth week videos, so that I have to see first. But here I understood the problems.
Okay, okay, fine. So if you're having doubt, you can ask in like I will be uploading video now. You can ask in comment section also. I can feel free to answer there as well.
Okay, sure.
So thank you.
Thank you so much.